Well, now we move on to question number 12, and if you had trouble in this problem, I would suggest that you also take a look at question number 11, because in that question I had discussed about the average velocity, not just the velocity, the average velocity between 2 points. So in this question, the particle starts from point A right here, and then it travels along this curve. We need to find out a position B. It can be B, can be here, can be here, can be here, can be here, can be anywhere, such that if you find that velocity, the property of that point will be that the average velocity between this point, and let's say that point lies here, point number B, and the average velocity between A and B has the same direction as the instantaneous velocity at B. What I would suggest, anytime you see these solutions, make sure you have a pen and a paper. So as I tell you to do some exercise, pause the video, do the exercise, and come back and check. So here the exercise for you is, look at the point B and try to find out what is the average velocity between A and B when it travels from A and to B, and the instantaneous velocity at B. And then if you know these two things, obviously you can find out, and the question is whether at point B the direction of the velocity is the same as the instantaneous velocity. While you do this, I will prepare another graph to make you understand about the average velocity and the instantaneous velocity. So in this figure I am showing another graph where there are 2 points P and Q, and the body moves from point P to point Q. What I say is that the average velocity between point P and Q will be given by the direction of that velocity will be given by the straight line joining P and Q. Why is it so? You can consult into question number 11. The only difference will be here you will take, in that calculations you will take the vector. The next thing I want to say is, what is the instantaneous velocity at P? How do we find the instantaneous velocity at P? The instantaneous velocity of P, you start moving this Q point a little closer, then this direction of this velocity is like this. If the point Q moves even further, it comes here, its direction is this one. This line just joining above this curve. If this point is Q, it's a little above this curve. We keep moving this point Q and making this distance, this delta, as small as possible till we reach the point P. What happens is point P. At point P, the points are very next to each other, and the direction of this velocity is along the tangent of this curve. Now we know these two things. We are trying to find out what happens at this point B. We join these 2 points, and then the velocity at B is pointing downwards in this direction, and the instantaneous velocity at B is along the tangent joining B, so it is in this direction. Those two directions are different. Let us consider some more points. Maybe you can think that this is the point which has the same direction, because this is at the lowest point. Maybe this is the answer. Why join this point from here? So the direction is in this one, and the instantaneous velocity at this point is in this direction. They are also different. How about anywhere somewhere around this point? Let us say we assume that the solution is somewhere along here to here. I join this point. the direction of the average velocity is along this direction, and the instantaneous velocity is this. The gap between the instantaneous velocity and the point joining has reduced, but there is still a difference. If I move to this point and join this, and this one has this direction, while the instantaneous velocity is this one. The gap in the direction is about the same, but still they are different. If you keep moving on this direction, this direction, the instantaneous direction will start moving this, and this direction will start moving, and they will start converging right at the point A. At point A, both of them have the same direction. But that is not the answer. We need to find some point other than A where the directions are same. So let's examine somewhere like here, the point here. If I join this and assume that this is the point, and this has the direction here, and the instantaneous velocity is along the tangent of this curve. You're trying to touch this curve. They have a different direction. But look at this point somewhere here. I will put a scale. I have a scale with me, and I take this scale ruler and I join this here and try to touch this curve. And I join a line like this. The line has a property that it just touches the curve at this point. In this case, the average velocity between A and B has this direction. And the instantaneous velocity at B also has this direction. So B is the point found by putting your scale and trying to keep one end here and other end just touching this will be the point where the instantaneous velocity and the average velocity will be the same. And this point has approximately at 5 meter, and this I think is at 3 meter. The coordinates will be 5 and 3. This should be enough for you, but I will suggest you an exercise. And the exercise is prove that the average velocity, the direction of the average velocity has the same direction between 2 points along an arbitrary curve in an x, and y direction. There is an arbitrary curve. The direction of the average velocity between 2 points A and B. How do you find the average velocity, average direction? You take this direction, you take this direction, you take this direction, you take this direction, take the average of these. And then you find that the direction of the average velocity is the same as direction of the line joining A and B. You can take the help of the explanation I gave you in the previous lecture. I hope this helps you. If you have any questions, you can also do it in the comment section. Thank you.